So our next speaker is Yifei Yuan on the new evolution of, and I'm going to mispronounce Hoyan, enhancing scalability, usability, accuracy of the Alibaba global WAN verification. Thank you, Yifei.
Okay, thanks for the introduction. I'm very excited to be here and share some experience about the evolution of Hoyan, which is a verification system deployed for Alibaba's global WAN. This is a collaborative work among many teams and colleagues as shown here. This work would not be possible without effort from all of the excellent colleagues. First of all, as one of the biggest cloud service providers, Alibaba Cloud operates a global wide area network that serves billions of people. By the end of 2024, this WAN interconnects tens of data centers, has more than 2,000 routers, and hosts millions of prefixes. To ensure the availability and the reliability of this WAN is extremely important. However, to operate such a hyperscale WAN is very, very hard. As shown here by our statistics several years back, actually 56% of the network incidents are caused by configuration update errors. So in response to that challenge, we initiated the Hoyan project in 2017. At a very high level, what Hoyan does is to run role simulation for the network after the change, given the network snapshot, the configuration update, and also the roles injected into the WAN. And the goal is to generate the RIPs after the change. So after we generated the RIPs, then Hoyan runs verification to check properties. At that time, the major properties Hoyan supported is reachability properties, such as routes from a router A can reach a router B. And we basically support BGP and IGP at that time. And then from 2020 to 2022, we gradually built traffic simulation and the verification capabilities into Hoyan. Because at that time, traffic load-related problems become one of the major incidents on the WAN. The idea is that given the input flow and generated RIPs from our role simulation, we can simulate the forwarding path of all the flows and then calculate the traffic load on each link after the change. Once we finish the computing, we have the traffic path and we have the flow path and we have the traffic load. Then we run verification against it. So in addition to reachability properties, we also add traffic load properties. And then we add the support for policy-based routing and segment routing. Starting from 2023, we have more evolution. Previously, Hoyan mainly supported the verification for the network after the change. And then we realized we really want to reason about the change between the network before the change and after the change. So we built a specification language called Vela. This was also published last year. At a high level, our operator can use Vela to specify the change intents. And then we use our results from the traffic simulation to check whether their specification can meet the results can meet the specification. So the intents are basically, we call this flow path change intents, such as flows used to be a path A should be now shifted to path B. So Hoyan's evolution didn't stop there. There are two major driving forces for the evolution of Hoyan. The first is a rapid evolution of our WAN. Starting from 2023, we started deploying the next generation WAN, building on top of new techniques such as segment routing v6. So this not only increases the size of our WAN, but also introduces a bunch of new features. The second driving force is ever-increasing operational requirements. Our operational team posts higher requirements to Hoyan in order to have a higher coverage for the prefixes and also other change scenarios. So as a result, we have new challenges on the scalability, usability, and accuracy This is what I'm going to focus in this talk. So first of all, scalability. So since the very beginning of Hoyan, the size of the network we supported increases 3 times, from a few hundred to more than 2,000. Looking future, we also want to support the data center networks in addition to the one as required by our operational team. This would add another order of magnitude to the network size. And also, the number of prefixes that Hoyan supported increases 2 orders, from tens of thousands to millions. The reason behind that is we previously only support high priority prefixes, but now we have to cover all prefixes on the one, which are millions. And the newly introduced traffic simulation also requires Hoyan to efficiently simulate billions of flows. But the requirement for the simulation time actually dropped significantly to hours, from hours to minutes, in order to support very urgent change verification requests. As a result, the original Hoyan cannot work for such a scale. So this figure shows the raw simulation time of the original Hoyan, which runs the simulation on a single machine. As you can see on the blue line, to simulate all the prefixes on the one, the original Hoyan needs more than half an hour to complete the simulation. If we add data center networks into the one, which will make the size to be tens of thousands, basically we cannot simulate more than 40% of the prefix on one machine. So to improve the scalability, probably the most natural idea is to shift it from a single machine architecture to a distributed architecture. So instead of running the simulation on a single machine, we can run the raw simulation and the traffic simulation on multiple machines to accomplish one simulation task. This is exactly what we do. I'm going to use this example to illustrate the high-level idea. For instance, we have this simple network. We have 3 routers, and we have to simulate the 6 routes with 5 prefixes. And as an example, I'm showing you here is the routing table for router A that is generated by the simulation. So as the route simulation basically follows a per prefix level, we can very simply distribute this task following prefix level. For instance, the first task here will simulate the prefix for 10/8 and the 40/24. And the second subtask will simulate the prefix for all other prefixes. So we can use 2 machines for the 2 subtasks. And we can see that each subtask will then generate a part of the routing table, and collectively they will generate the whole routing table for the routers. So once we have generated the routing tables, doing the distributed traffic simulation is very similar. So consider again, we have a network here, and we have to simulate the forwarding path for the 6 input flows. So we can naturally split the 6 flows into 2 subtasks. Each subtask will simulate 3 flows. For instance, the first subtask simulates the flows 10.1, 20.1, and 20.2. And the second subtask would simulate all other flows. So since our goal is to compute the forwarding path and the traffic load, so each subtask will compute the traffic load only for the simulated flows. And the real traffic load on a link will be the sum across multiple subtasks. Actually, this is very good, except there's one problem. We're assuming that we know the entire routing table already. But remember that we have millions of prefixes, and we have thousands, even tens of thousands of routers. Loading all the RIBs into a machine would not work. So if we look closer, actually we do not need to load all the RIBs into a machine. For instance, to simulate the traffic, simulate the 3 flows for the first traffic simulation task, we only need the routes for 10/8 and 40/24, which is in the second row simulation task. But to simulate the rows 20.1, we also need the rows 20/8 from the second row simulation task. So there's a dependency over there. So the question is, can we reduce this dependency in order to reduce the number of ribs we need to node? For this question, we use a simple heuristic. We order the prefixes from the smallest to the largest by the last IP address in them. We also follow the same order to order the flows. In this way, in the first row simulation task, it will simulate the prefix 10/8, 11/8, and 20/8. So that the first traffic simulation only depends on the first row simulation, and we only need to load the first rib from the first subtask. So this is a performance evaluation. On the left-hand side, I'm showing you the row simulation time. For the one, we can achieve 5 times speed up. And if we add in the data center networks into the one, we actually can simulate all the network within 25 minutes. For traffic simulation, we achieved 4 times speed up. And if we remove the heuristic, as I just mentioned before, they're actually going to be a 52% larger running time, which shows the effectiveness of the heuristic. By the way, I should mention we use 10 machines for the distributed simulation. Okay, the second challenge is about the usability. So this figure shows all the change types that the operational team requires to support. So as you can see on the third column, the intents of the changes differ significantly from each other. By looking into past years' changes, we can actually identify 3 types of change intents, as shown on the second column. The first type is we call is flow path change intents, such as flows on path A should be moved to path B. For this kind of intents, we designed the RELA, the language, to specify and verify such intents. And the second type of intents, we call this traffic load changes, such as there's no overloading after the change of the network. So these type of intents are usually simple, and we can easily specify them using a range of the desired traffic load. And the third types of intents, we call this role change intents. Something like the roads with community C1 should now be changed to have community C2. For this kind of intents, we use to hard code the verification logic into our software, or we rely on manual inspection, which are both error-prone and time-consuming. So the key idea here is that we want to design a language to capture such a type of intents. We call this language RCL, role change language. And after thorough discussion with our operation team, we decided that the design goal of a language is on the ease of usage instead of general purpose querying such as SQL. But still, we want to cover most common role change intents. So to illustrate the idea of RCL, I'm going to use this very typical change intents. This intent has 2 sub-intents. The first sub-intent is that roads with prefix 10/24 should have local preference 300 after the change. And the second sub-intent is that other roads should remain unchanged. So first of all, for language, we need to understand what's the underlying abstraction. So our abstraction is called global rib abstraction. Basically, you can think of it as one big table of all roads in the network. We have 2 additional fields called the device and verb, which indicates where the road located. As I'm showing here are examples of the global rib before and after the change, and we refer to them as pre and post. So now let's consider the first sub-intent. To specify such intent, our first step is to get all the local preference values from the after change rib. For this, we can first use the distributed values expression to get all the local preferences, and then we apply that to post, which is after change rib, which gives us all the local preference values from the after change rib. And then we want to assert that the only value is 300, which is easy by using this equality check-in. And then last, we want to specify our scope, which is all the roads with prefix 10/24. We can easily specify as shown here, which completes the specification of the first subintent. To specify the second subintent, it's even simpler. To specify that the rib remain unchanged, we can simply say pre is equal to post. And then we can add the desired scope, which is prefix not equal to 10/24. Of course, we have the formal syntax and the semantics in the paper. Please read the paper for more detail. So we have deployed RCL on our WAN for more than 1 year. And it has been used on a daily basis and supports tens of changes each week. And it covers most route change intents so far. And the figure here shows the evaluation. On the left-hand side, I'm showing the CDF of the specification size. As we can see here, most of the spec of the intents are small. And on the right-hand side, I'm showing the performance of the verification. And you can see that 80% of the specs can be verified within 1 minute, which is very efficient. Okay, lastly, I'm going to very briefly talk about the accuracy. So the challenge here is that since we have new features such as segment routing version 6, and we also have this traffic simulation introduced 2 years ago, the original Hoyan's accuracy diagnosis framework for roads does not work. So we enhanced that framework by validating the accuracy for both roads and traffic with a live network, and also have a semi-automatic root cause analysis to understand the root causes of the inaccuracy. By using this approach, we can cover a lot of real-world issues as we summarize it here. Unfortunately, I don't have time to go through them one by one, but you are encouraged to read the paper for more detail. Okay, so for the deployment experience, with all these evolutions, so now each week, Hoyan now supports tens of manually triggered verification requests and hundreds of automatically triggered verification requests. And each year, Hoyan was able to uncover tens of change risks, some of which would lead to severe incidences. But luckily, we have Hoyan, we can prevent them in advance. And as a result, we reduced the misconfiguration cost network incidents from 52% to 5% on R1. So we identified a large set of root causes we summarized in the table, and you can also find the use cases in the paper. We encourage you to read the paper. To conclude, I'm presenting the evolution of Hoyan on using distributed simulation, the RCO language, the accuracy diagnosis framework to address the scalability, usability, and accuracy challenges. And Hoyan is used in Alibaba Cloud on a daily basis and prevented tens of network incidents each year and helps reduce misconfiguration costs network incidences from 56% to 5%. With that, I'm happy to take questions.
Thank you for that insight into what is a fantastically growing system. So questions from the floor. I might ask, if you are going to ask a question, could you stand up? It's actually impossible for us to see who's asking a question from up here. So do we have someone who'd like to ask questions from the floor? We have someone who needs a microphone, please, and stand up. Thank you.
Hi, Ife. This is Siva Kakala from Microsoft. I'm curious, you mentioned U. So is the traffic load violations still part of this, or U is a separate system?
What's that? Per packet?
The traffic load violation verified.
Traffic simulation.
The U from last year's SIGCOMM', is that part of Hoyan, or it's a different system that you verifies traffic properties separately?
Oh, last year we presented the relational network verification thing. Okay, that is about the specification for flow path change intents. Yeah, we consider it a part of, we integrate that into Hoyan.
I was asking about the U, YU, the traffic load properties.
Yes, it's also integrated into Hoyan.
But if I remember it kind of did symbolic simulation to figure out what are the failures that can result in traffic load. But Hoyan feels like a concrete...
concrete simulation.
Yeah, so can you handle the cases like you did where are there failures that can lead to traffic violations with Hoyan?
If I understand your question, you are talking about the difference between symbolic and concrete?
Yes.
Okay, so we use concrete simulation for flows, and the symbolic thing is to encode the failures, not for the flows.
Okay,
Yeah.
got it, thank you.
And another question here at the front, please. Just hold it up to your mouth.
Thank you for the great talk. So my question is about when we verify a new network change intent, and there are some conflict between the new network change intent and the existing configuration, say verification is failed. How can we identify which configuration causes for the conflict?
Oh yes, so this is a very good question. So a lot of conflicts, I'll give concrete examples. For instance, if your change refers to an undefined prefix, for instance, that's obviously invalid, right? Conflict. We can check such things beforehand in our tool. I didn't have time to present that, but there is a use case talking about such cases. For other conflicting things, for instance, if you, because of the bugs of the software, you cannot understand the command, this is totally out of the scope of the simulation. We have our other tools to handle such issues.
Okay, thank you.
Sure.
And do we have any further questions from the floor? And then I'm going to prompt you with a very short one of mine, which was, did you see, it's the opportunity to tell us where you saw the problems, were you seeing systematic issues arising in configuration? For example, differences between equipment's interpretation and firmware interpretations and so on. Perhaps an insight into that very large number.
Yeah, so you can see here, we have a column here, we call this VSB, vendor-specific behavior, which is exactly what you're talking about. We uncovered tens, even, I don't know, there's a table in our paper, a lot of VSBs we uncovered. Yeah, certainly there are a lot of them, but yeah, I don't have time to present it, but it's in the paper, yeah.
Excellent, okay. Thank you very much for joining us, thanks.
Thank you.